Benzyl acetate is an ester that is naturally occurring in many flowering plants and can be synthesized in the lab using the reactants acetic anhydride and benzyl alcohol. It can be used as a food additive, flavoring agent, and odor agent as a result of its flowery scent. Benzyl acetate is primarily used in soaps and air fresheners, but is not limited to other household cleaning and personal products.
The challenge explored in this lab was the synthesis of benzyl acetate without the use of an acid catalyst. The synthesis reaction without the acid catalyst reacts at a very slow rate, which is why sulfuric acid is typically used to catalyze product production. Our goal was to increase the rate of reaction without using an acid catalyst by applying our knowledge of kinetics and thermodynamics.
Looking at the reaction path diagram for the synthesis reaction, we came to the decision that the products acetic anhydride and benzyl acetate are higher in potential energy than the reactants acetic acid and benzyl alcohol. The higher potential energy state, in this case the products, is favored to be produced at higher temperature. This is because an input in energy, heat, gives the molecules in the lower potential energy state the ability to overcome their strong interactions with one another and move to the higher potential energy state. Thus, we decided to run the synthesis reaction using reflux.
Furthermore, it was decided to try an additional synthesis using a base catalyst. The reasoning behind this was that if the reactants in the slow step are destabilized, then the reaction will proceed at a faster rate. The production of charred species using a base catalyst results in the instability of reactants. Because reactants would be higher in potential energy, the same products are being formed, the activation energy would be lowered only in the forward direction.
Also, we deduced that the extent of the synthesis of benzyl acetate could be increased by reflux and by a base catalyst. To implement these designs, we conducted 3 separate experiments. First at reflux, second with a base catalyst, and third with both a base catalyst and done at reflux.
In lab, the synthesis at reflux was done by adding 2.0 milliliters and 1.5 milliliters of the reactants acetic anhydride and benzyl alcohol respectively. After the solution was stirred for 20 minutes, it underwent reflux for 1 hour and was worked up with a series of mixing and extraction with water, sodium chloride, and sodium bicarbonate, followed with addition and filtering of magnesium sulfate.
The design for the synthesis with a base catalyst similarly followed the procedure to the ones for the synthesis at reflux. The solution of benzyl alcohol and acetic anhydride was not put on reflux, but had 10 drops of sodium carbonate added to it.
The same procedures were followed for the synthesis that underwent reflux and had the base catalyst sodium carbonate added to its starting solution. Reflux was, however, done for 15 minutes. FTR spectrum of the base catalyst was analyzed to find a signal for a C-O for esters at 7040.75 inverse centimeters and a C-O signal for aromatic esters at 1230.90 inverse centimeters. These signals are unique to the ester molecule, benzyl acetate, that differentiate it from the 3 other substances in the reaction: benzyl alcohol, acetic anhydride, and acetic acid, indicating that FTR is evidence for the presence of benzyl acetate.
For the reflux synthesis of benzyl acetate, analysis of its FTIR spectrum found that there was a signal for the C-O bond for esters at 1740 inverse centimeters and a CO bond around 1235 inverse centimeters.
For the FTR spectrum of synthesis that had both base catalyst and reflux, it had signals indicative of the ester C-O and aromatic ester C-O at 1741.12 centimeters inverse and 1230.99 centimeters inverse, respectively.
Our NMR was successful in indicating benzyl acetate. The D signal at a shift of 1.95 ppm is likely the methyl group on the end of the molecule. Signal B represents the CH2 group between the benzene ring and the ester. Finally, signal A shows the CH groups on the benzene ring, as well as the solvent P.
The NMR results for the base catalyst reaction is evidence of the presence of benzyl acetate. Signal A is indicative of the CH groups in the benzyl acetate benzene ring, and signal B is representative of the CH2 groups in the benzene ring and esters of benzyl acetate, while signal C is indicative of the CH3 groups at the end of benzyl acetate.
In conclusion, our synthesis of benzyl acetate was successful for both the base catalyst and the reflux base catalyst, as well as the regular reflux synthesis. After having undergone the workup processes for all 3 synthesis reactions, the IR and NMR data indicated that the ester benzyl acetate was produced.